Hi, my name is Haishan Zhu. I'm very glad to work with Professor Todd Austin and the PhD student Jason Clemens this summer on SURE project called Do You Hear What I See? It has been a wonderful experience and I benefit a lot from it. Okay, now let's get started.
The World Health Organization estimates that approximately 2.6% of the human population is visually impaired. This research proposes to help the visually impaired to navigate an indoor environment by using sensors and visual sonification. Visual sonification is the process of transforming visual data into sound, which would non-invasively allow a blind person to see their surroundings in real time using their sense of hearing. In order to achieve this purpose, we are working on multidisciplines ranging from computer vision, audio processing, to computer architecture. My focus in this project is to assess the efficiency of some specific computer vision algorithms on current processors and propose possible improvements on computer architecture. Many computer vision algorithms are adopted to extract useful information from sensors. Specifically, we are interested in feature extraction, feature classification, multi-image processing, and recognition applications. Features are key characteristics of a scene. Typical image features include corners, edges, intensity gradients, shapes, and blobs. Feature extraction is the process of locating features within a scene and generating signatures to represent these features. This is a key concept of most computer vision algorithms. Once feature descriptors are extracted, there's typically a reasoning process that takes place based on these features. A common component of this reasoning phase is feature classification. Feature classification attempts to predict some information about a feature based on the descriptor. The classification will commonly use previous data to make predictions about the new data. Multi-image processing is commonly used in embedded vision applications. Multiple images or frames are used to get information about a scene. For example, tracking can be used in robotics to follow mobile objects. Other recognition applications utilize vision kernels, such as feature extraction and classification, to analyze images or scenes. For example, augmented reality will first find a marker from the image and project figures onto the scene with appropriate translation and rotation relative to the camera. Computer vision algorithms are often computation intensive. Furthermore, they usually share some specific features. It would help the performance a lot if we can improve the computer architecture based on these features. So what are the features that computer vision algorithms share? There are at least three of them: repetitions, memory access pattern, and thread-level parallelism. As a common case, computer vision algorithms usually go through the input image several times with some kind of repetition. We could exploit this feature by introducing custom functional units. Common repetitions in these algorithms include one-to-many comparison, convolution, and 2D gradient unit. In one-to-many compare, one value is compared to other data from an image. In this case, the result is the logic AND of each compare. In convolution, data in two vectors are multiplied element-wise, and the results are summarized. In 2D gradient unit, the result is calculated by summarizing the difference of data in both horizontal and vertical directions. While these operations are common in vision algorithms, they are all essentially repetitions of some simple instructions. It could help efficiency a lot if we can issue a vector of this instruction in a single cycle instead of issuing same instructions for tens or hundreds of cycles. As you may notice in 2D gradient unit, the algorithm needs data from a small area of an image. This is true for many other operations. However, images are conventionally stored in memory by row rather than by area, and since memory is organized in rows, accessing any row of memory takes a fair amount of time. Assume a row of the image is stored in a row of memory as shown here. To get a small area of an image, the processor has to access different rows in memory, which could be hundreds or thousands of cycles. Given the memory access pattern, we come up with the idea of patch memory, in which an area of data is stored in memory. Now as long as the size of the window is appropriate, only 4 rows of memory will be accessed at maximum, which will significantly shorten the memory access time. Finally, we noticed that operations on different areas of an image are usually independent of each other. The absence of dependency indicates that these operations can be handled on different cores at the same time. We can exploit this feature by using heterogeneous multicore. In this case, we have a complex core in the center surrounded by 8 simple cores. The complex core will first divide and distribute the work for each simple core before starting to do his own job. After calculation is done, it will collect results from each core, summarize them, and determine what to do next. To validate these proposals, we developed a benchmark suite and simulated its performance on different computer architectures. Here is a list of algorithms that we included. We used several different ways to simulate the behavior of the processor when running the code. Besides running the benchmark on bare metal of embedded and desktop cores, we also use a simulator to get more detailed data and statistics. It is my job in this project to modify the simulator and calculate and record specific data. The simulator we are using is called Mars X86, which is a cycle-accurate full system simulator. It is modified to get some unique data like branch divergence, patch memory hit rate, and multi-core memory statistics. We also use other tools to analyze hotspots, or the most executed code of each benchmark to understand these algorithms. From simulation results, we concluded that most of the listed algorithms would benefit from parallelism. Hotspot analysis, on the other hand, showed that most executed code is usually vector operations. But the high control complexity leads to hinder the performance of traditional vector machines. Thus, custom functional units may be a better fit. Also, we find that patch memory performs much better than traditional memory as in terms of L2 hit rates in most applications. We put together all the work into the paper titled MathBench, a mobile computer vision benchmarking suite. And this paper has been accepted by IEEE International Symposium on Workload Characterization. The publishing of this paper nicely concluded this project.
Finally, I would like to thank Professor Austin and the SURE program for this opportunity. The project gives me the chance to explore, to fail, and to think in different perspectives. I really enjoyed this summer.